Welcome to Talk Tensors, where we unpack the latest, really interesting research in machine learning.
Great to be here.
Today, we're diving into a paper called KUDA, Keypoints to Unify Dynamics Learning and Visual Prompting for Open Vocabulary Robotic Manipulation. Quite a mouthful.
It is, but the core concept is actually pretty intuitive, I think.
Yeah, it's all about getting robots to, understand and act on everyday language instructions, like just telling a robot, stack these things, even if these things are objects it hasn't seen before.
Exactly. That kind of open vocabulary skill where the robot isn't limited to a predefined set of objects or tasks. It's been a huge goal in robotics for a long time.
For sure. And it's tricky, right? Bridging that gap between our abstract language and the physical world, the actual actions a robot needs to take.
It really is. And, we see huge strides recently with large language models, LLMs, and vision language models, VLMs. They're much better at understanding what we mean.
But there's been a catch.
A big one. Most of these systems, they don't really grasp the physics, the dynamics of how objects actually move and interact.
Right. So they might understand stack and they can see the objects. But if it's not just like simple wooden blocks, if it's something deformable or wobbly or a pile of something.
They struggle. They often treat everything as rigid or only manage very coarse movements because they lack that deeper understanding of dynamics.
And that's where this paper, KUDA, comes in. It proposes something pretty clever.
It does. They introduce this idea of using key points. You can think of them as specific identifiable points on an object that the system can track.
Okay, key points.
And the key insight, the really neat part, is that these key points act as a sort of shared language, a common ground.
Shared between what?
Between the vision language models, which are good at the visual understanding and interpreting language, and the dynamics models, which are good at predicting how things will move the physics.
Ah, I see. So the VLM looks at the image, sees the key points, and figures out where they should go based on the instruction, like make this rope straight.
Precisely. It can reason about the desired spatial relationship between these key points. Maybe point A needs to be further from point B.
And then
that desired arrangement of key points gets translated into something the dynamics model can understand, like a target state or a cost function.
A cost function, like how far away the current state is from the desired state.
Exactly. The dynamics model then uses this target, along with its knowledge of physics, to plan the actual robot movements needed to get those key points where they're supposed to be.
That's really elegant. It connects the high-level understanding to the low-level physical action through this intermediate representation.
It does. The KUDA system takes the language command and what the robot sees.
The visual observation.
Right. It automatically finds these key points, puts labels on them, then the VLM, which they actually boost using a few examples.
Like few-shot learning.
Yeah, exactly. It figures out the target configuration for the key points. That becomes the goal for the model-based planner, which uses the pre-trained dynamics model to figure out the robot's actions.
And you mentioned feedback.
Yes. There's a closed-loop control aspect, too, which helps correct errors during execution, making it more robust.
It sounds pretty comprehensive. Did they test it much?
They really did. The paper shows results across a whole range of tasks. Different language instructions, different objects, rigid cubes, sure, but also deformable ropes, even granular stuff like coffee beans.
Coffee beans, that's tricky.
Very. And tasks involving multiple objects interacting. They also have a project page up, which is great for transparency and letting others dig in.
Okay, so before we dive deeper into how KUDA works, maybe let's take a step back, put this in context. How do we get to needing something like KUDA?
Good idea. Well, the dream of robots understanding natural language isn't new, obviously. It goes way back.
Early robotics was more about like factory arms doing the same task over and over in a cage, right? Very pre-programmed, very rigid environments.
Exactly. Highly structured. Then AI and machine learning started to develop, especially in perception, letting robots see and react more. But language was always this intuitive, flexible interface we wanted.
Kind of paralleling the work in NLP, trying to get computers to understand text.
Very much so.
Yeah.
And the recent boom in large models, the LMs and VLMs we mentioned, that felt like a potential breakthrough moment for robotics, too. Suddenly, models could understand language and visual scenes way better than before.
Like we saw with computer vision and NLP individually hitting these big milestones. Now, applying that power to robots seemed obvious.
It did, but as the KUDA authors point out, and as we've discussed, just plugging in an LLM or VLM isn't enough. There's this grounding problem.
Grounding the abstract language, the visual perception, into the physical reality of forces, friction, object properties.
Precisely. How do you get from pick up the soft toy carefully to the specific sequence of joint torques that achieves that without crushing the toy? Many systems based purely on these large models tended to skip over the dynamics.
They focused on the what, but not the how in terms of physics.
Right. And KDA's approach, using key points to explicitly link the VLM's understanding to a dynamics-aware planner, is a direct attempt to solve that grounding problem. It's about making the robot's actions physically plausible and effective.
It feels like a step beyond just reactive systems or purely language-driven planning, integrating that learned physics knowledge.
Definitely. It's tackling that core challenge of generalization and adaptability, but grounding it in physical interaction.
Okay, so let's recap the core KUD ideas, make sure we've got them clear. The absolute centerpiece is using key points as this common language.
Yep. Understandable by the vision side, usable by the physics side.
And this lets them specify tasks flexibly using language, but plan actions accurately using learned dynamics.
Correct. And critically, they don't just rely on the VLM getting it right the first time from scratch. They use this smart prompt retrieval system.
The Top K prompt library.
Right. It finds the most relevant examples from a pre-built library to show the VLM, which helps it understand the current specific instruction much better. It leverages that in-context learning capability.
Which is powerful. And then there's the control system.
The two-level closed-loop control, that's key for robustness. It means the system can notice if things aren't going quite right and adjust.
Adjustments both at the high level, like maybe the VLM needs to rethink the target points.
Exactly, maybe based on a new view after an initial move.
And at the low level, the actual robot motion control adapting to errors.
Yes, which is crucial because the real world is never quite like the simulation.
And the results seem to back this up. You mentioned it outperformed others.
Significantly, according to their experiments. They compared against other methods like MOK and VoxPoser on several tasks, different objects. KUDA generally had much higher success rate.
Why the big difference?
The paper argues it's because those other methods often lack that detailed representation, like key points, or they don't explicitly model the dynamics, especially for non-rigid things. KDA's combination seems to be the key advantage.
That makes sense. Were there things KDA didn't do well on? Any limitations?
Oh, absolutely. And they're upfront about them. Perception was a big source of failures.
Like just not seeing the objects correctly?
Yeah, errors in segmenting objects, especially when they were overlapping or really close together. That accounted for about half of the failures in their analysis.
Okay, so perception is still a bottleneck. What else?
Sometimes the VLM didn't specify the targets quite right, maybe underspecified. Tracking key points could fail, especially in dense piles. And of course, the dynamics models themselves aren't perfect. And there's always the sim-to-real gap.
Right, training and simulation and then deploying in the real world always introduces challenges. The physics are never quite identical.
And they also mentioned the limitation of using only a top-down camera, which makes complex 3D spatial reasoning harder.
So lots of areas for future work, but the core idea seems really promising.
Definitely. This approach of unifying the visual prompting with dynamics learning via key points feels like a really important direction.
All right, so we've got a good handle on KUDA, its context, and its performance. Let's shift gears a bit into our novel notions segment. Where could this kind of research go next?
Okay, let's speculate a little. Building on KUDA's core idea, what if we push that unification even further?
How do you mean?
Well, right now, KUDA uses a VLM for understanding and a separate pre-trained dynamics model for physics. What if the VLM itself could learn to predict the dynamics?
Learning key point dynamics directly from visual prompts. So the same model doing the visual understanding also predicts how the key points will move.
Exactly. Instead of just predicting target locations, it predicts the outcome of actions on those key points. We know VLMs learn incredible amounts about the world from their training data, including visual physics, implicitly.
So if you showed it sequences like, here's the visual input, here's the language command, here's the action taken, and here's how the key points moved, maybe it could learn those relationships.
Potentially. Its understanding of spatial relationships is already strong. By seeing enough examples, maybe through in-context learning like KUDA already uses, it might infer the underlying physical principles governing those specific key points in that context.
That would be a much tighter integration. The understanding and the predicting physical consequences would be intertwined in the same model.
Right. It might leverage its general world knowledge as a strong prior for physics. Imagine not needing to train a separate dynamics model for every new object type. The VLM might generalize better.
Now, that feels ambitious. Fully replacing dedicated dynamics models seems like a stretch in the near term.
Agreed. Probably low probability for a full replacement soon, but maybe medium probability for hybrid approaches, where the VLM helps predict some aspects of the dynamics or helps adapt a general dynamics model to a specific situation described in language.
That seems more plausible. Interesting. Okay, here's another angle. Interaction. What about interactive refinement using language feedback?
So letting the human jump in.
Yeah. The VLM generates the initial keypoint targets, the robot starts moving, but maybe it's not quite right. Could the human then just say, move that top keypoint a bit to the left, or pull those 2 points further apart to make it straighter?
That taps into the VLM's language understanding again, but for real-time correction. It combines the robot's attempt with human intuition and fine-grained guidance.
We've seen other work where language feedback helps correct robot plans, right? Applying it specifically to these visual key points feels very natural. Humans are good at spatial reasoning and giving directions.
It could make the system much more precise, especially for subtle or complex tasks, where the initial VLM specification might be slightly off, or where the dynamics lead to unexpected results. It turns it into more of a collaboration.
A human acting as a high-level supervisor, using intuitive language to guide the physical manipulation through these key point targets.
Yeah, I could see that being really powerful. What's the probability? Maybe medium. I think we'll definitely see more research into interactive language feedback for robots, and key points seem like a really good handle for that interaction.
It definitely feels like a practical way to improve robustness in the near term.
Of course, standard disclaimer applies.
Right.
These are just speculative ideas, food for thought based on the paper. Research might go in totally different directions.
Naturally. But KUDA definitely provides a solid foundation to build upon. This unification of language, vision, and dynamics really does feel like a crucial step forward for robotics.
It addresses a core limitation and opens up possibilities for robots that are much more versatile and capable of handling complex, real-world tasks based on our instructions. The key point representation seems particularly potent.
We definitely recommend checking out the paper itself link in the show notes if you want the full technical breakdown. It's a well-executed piece of work.
And it leaves us with that bigger question, doesn't it? As robots get better at understanding our language and interacting with the physical world, how does our relationship with them change? It goes beyond just giving simple commands.
Indeed. Something to ponder. Thanks everyone for joining us for this deep dive on talk tensors.